All right, let's briefly talk about chemical equilibrium. And we're going to talk about multiple reactions and yield and selectivity in the same lecture to try and make this nice and quick for you. So there are two big questions in chemical reaction engineering. Given a set of reactants and conditions, one of the first questions we'll ask is, what is the equilibrium, concentration, sure. And this is what we call chemical equilibrium thermodynamics. So you may have seen this in chemistry, most likely in Chem 1 and Chem 2, maybe a little bit in a thermodynamics class if that's something that you've taken. And then the other question that we tend to ask ourselves, which is something that you'll learn more and more as you go further through your environmental engineering career, is how long will the system take to reach equilibrium? And this is the study of chemical kinetics. So there's two different things that you can end up studying. So a lot of times we hope that things are in equilibrium because that's easier for us to deal with, but many times we need to reach equilibrium. So if you think about environmental engineering systems and you have a reaction occurring, this is like almost like the startup phase of many of our processes that we have, because we have to reach to equilibrium. So we have to have some kind of a startup phase. And then if we're in kind of a steady state operation, we're normally at this equilibrium concentration of a mixture. So these are kind of two different status points when it comes to chemical reactions in real world systems. The other terms that I want you to be aware of are irreversible reactions. And these are reactions that only proceed in a single direction. So the concentration here of the limiting reactant will eventually equal zero. Irreversible reactions, they only go one direction. We can also have what are called reversible reactions. And reversible reactions, just like they sound, is you can go reactants form products and products can also form reactants. So that's the equilibrium sign where the arrows go in both ways. So chemical equilibrium occurs when the rate of reactions between the products and the reactants does not change with time. So we have stable amount going forward and a stable amount going backwards. Okay, so those are terms related to chemical equilibrium that are important to know. Next, we're going to talk about multiple reactions, yield, and selectivity. Move some stuff around. Although we want specific reactants to yield specific products, many times our reactants do things that we don't want them to do. So things like side reactions are going to occur and they can lead to economic losses. So it becomes more costly and complicated to achieve the desired result. And this is big in environmental engineering. Minimizing a loss of economic value is really important. So these are concepts that really kind of come from chemical engineering, but really have a big implication for us as environmental engineers. So this is important for us to know. So we're going to have two terms that we talk about here. The first is yield, and the second is selectivity. And these two terms are going to help us describe the degree to which a desired reaction predominates over competing side reactions. So we're going to define those two terms in this space below. So yield, if I can spell, is going to equal the moles of desired product formed divided by the moles formed if no side reactions occur. Right? So what that means, that term there, that means we have 100% consumption of the limiting reactant. That's what that means. And yield is a percentage. So we multiply this number by 100%. So yield is basically telling us, here's the desired product form. This is what we want in terms of moles. And this is the moles formed if no side reactions occur, right? So this is the yield that we want. And we want, there's a little note down here, we want high yields, right? A low yield is a bad thing for us. Yield is different from selectivity, but only by a little bit, so it's important to kind of understand the difference. So selectivity has the same numerator, so moles desired product formed. But this one is divided by moles of undesired product formed instead. And so this one is not expressed as a percent. You're always, for selectivity, going to have something in the form of moles of A per moles of B. And I'm going to move my paper just a bit so I have a little bit more room. What this means is it's the selectivity of A relative to B. So yield is a percent that tells us the moles of desired product form divided by the moles formed if no side reactions occur. Selectivity has the same numerator, moles of desired product, but it's divided by the moles of undesired product form. So this is a ratio, not a percent. And this moles of A to moles of B represents the selectivity of A relative to B. So for both of these, we want relatively high values. We want high yield values and high selectivity values. So we'll put that into practice with one of our examples, example 4.9 in your notes in our next set of videos.